Hello, and a very soft welcome to the Whispered Lore. Settle in, find your comfort, and allow the sounds of your day to gently fade into silence. Tonight, we journey not to the roar of the Colosseum, but to the steady, quiet murmur of flowing water. We turn our gentle focus to one of Rome's most enduring and understated marvels, the aqueducts. We will be exploring the patient science behind their incredible design, tracing the meticulous art of gradient surveying that allowed water to travel for miles. We will also drift through the quiet, dedicated protocols of their maintenance, the constant, careful work that kept civilization hydrated for centuries. So, close your eyes and let the details of this ancient, steady craft guide you toward a deep and peaceful sleep. The Roman world, at its zenith, was an entity defined not merely by its legions or its laws, but by a profound and deliberate reordering of the natural landscape. It was an empire of infrastructure, a civilization built upon the predictable and systematic application of engineering principles to solve the fundamental problems of urban existence. At the very core of this existence, underpinning the grandeur of the forums, the leisure of the baths, and the basic sanitation of a metropolis of 1 million souls, was a single vital substance: water. This is the story of how that water was tamed, transported, and delivered. It is the story of the Roman aqueducts, but more specifically, it is an examination of the two quiet, unglamorous disciplines that made them possible: the meticulous science of gradient surveying and the relentless necessity of maintenance. Before the advent of the great aqueducts, Rome, like any other ancient city, quenched its thirst from local sources. The Tiber River, the city's lifeblood and its sewer, offered a ready, if increasingly sullied, supply. Springs, such as the Fons Juturnae in the Forum, provided clearer water, often imbued with religious significance. And throughout the city's sprawling districts, innumerable wells were sunk into the earth, tapping the subterranean water table. For the early Republic, this was sufficient. But as Rome grew from a regional power to the master of the Mediterranean, its population swelled, its ambitions magnified, and its thirst became insatiable. The water of the Tiber was no longer potable for a city of its scale. The local springs were inadequate, and the wells were often contaminated by the very density of the population they were intended to serve. The problem was not merely one of quantity, but of quality and distribution. To build the monumental city envisioned by its leaders, with its vast public baths, ornamental fountains, and private villas, a new paradigm of water management was required. Water needed to be imported. The first step in this technological leap was the Aqua Appia, constructed in 312 BC by the censor Appius Claudius Caecus. Its creation marked a conceptual shift. Water was no longer a resource to be found, but a utility to be engineered. Significantly, the Aqua Appia ran almost entirely underground, a testament to the engineering caution of the period. It followed the contours of the land in a covered trench, a practical solution that protected the water from contamination and the channel itself from damage. But it established the fundamental principle that would govern all subsequent aqueduct construction: gravity. Roman aqueducts were, in essence, artificial rivers. They were not pressurized systems in the modern sense. They did not rely on pumps or siphons for their primary motivation. They functioned on a simple yet unforgiving law of physics. Water flows downhill. To transport water from a spring in the Sabine Hills, sometimes over 90 kilometers away, to a distribution tank on the Esquiline Hill in Rome, the entire length of the channel, or specus, had to maintain a continuous, gentle, downward slope. This is where the discipline of gradient surveying becomes paramount. The gradient could not be too steep, lest the velocity of the water scour the channel lining and cause erosion, particularly at bends. A fast-flowing current would be difficult to manage at offtake points and would place undue stress on the structure. Conversely, and more critically, the gradient could not be too shallow. If the slope were insufficient, the water would stagnate, allowing sediment to settle and block the channel. A loss of momentum over a long, flat stretch could halt the flow entirely, rendering the entire multi-million sesterce investment useless. Even a minor miscalculation, a deviation of a few centimeters over a kilometer, could be magnified into a critical failure over the full course of the aqueduct. The engineering vision that underpinned the Roman aqueduct system was not one of singular, revolutionary invention, but rather a profound and systematic refinement of existing principles. It was an exercise in scale, in precision, and in a deeply pragmatic understanding of the physical world. The Roman achievement lay not in the discovery of new hydraulic laws, but in the meticulous application of known truths across vast and challenging terrains. At its core, Roman hydraulics was an elegant and unwavering devotion to a single, dominant force, gravity. Every aqueduct, regardless of its length or the complexity of its structure, was conceived as an artificial river, a controlled channel designed to guide water on a continuous, gentle, and predictable descent. The fundamental parameter governing this entire system was the gradient. The selection and maintenance of this gradient, or slope, was the primary task of the Roman military surveyor, the agrimensor. The objective was to create a slope steep enough to ensure a constant and useful flow, preventing the water from stagnating and depositing silt, yet gentle enough to prevent the water from achieving a velocity that would scour and erode the channel lining. The acceptable range was remarkably fine. Surviving examples and the writings of engineers such as Vitruvius suggest an optimal gradient of between 1 part in 3,000 and 1 part in 5,000, which translates to a drop of a mere 20 to 33 centimeters for every kilometer of horizontal distance. This was a tolerance that demanded extraordinary precision over journeys that could extend for nearly 100 kilometers. The establishment of this shallow, consistent gradient was accomplished through a suite of sophisticated surveying instruments. The principal tool was the chorobates, a long wooden plank, perhaps 6 meters in length, supported by 2 legs. Its top surface featured a precisely carved channel. By filling this channel with water, the surveyor could ascertain a true horizontal level. For use in windy conditions, where the water's surface might be disturbed, plumb lines were suspended from the frame. When these lines hung perfectly parallel to the legs of the instrument, a level reading was confirmed. Another instrument, the dioptra, was a more complex device that could be used to measure both horizontal and vertical angles, functioning as a precursor to the modern theodolite. For initial layout and the establishment of right angles, the surveyors employed the groma, a simple cross staff with plumb bobs, which was essential for mapping the aqueduct's path and the surrounding topography. The process was painstaking. Sightings were taken from one point to the next, with wooden stakes driven into the ground to mark the intended level of the aqueduct's channel floor. This iterative process of measurement, calculation, and marking was repeated thousands upon thousands of times, from the water source, or caput aquae, to its final destination in the city. Once the path and gradient were established, attention turned to the construction of the conduit itself, known as the specus. The structural form of the aqueduct is often visualized as the monumental stone arches that cross valleys, but these sections constituted a small fraction of any given aqueduct's total length. The vast majority of the channel was a subterranean or ground-level construction. The specus was typically a rectangular channel, approximately 1 meter wide and 2 meters high, allowing for an inspector to walk through it for maintenance. The construction materials varied depending on local availability and the specific era of construction. Early conduits might be carved from solid rock or built from carefully cut ashlar masonry. However, the true Roman innovation was the widespread use of concrete, or opus caementicium. The construction of a Roman aqueduct was an act of profound ambition, an imposition of order upon a chaotic landscape. Its success was not contingent upon brute force alone, but upon an almost imperceptible, yet relentless, precision. The very lifeblood of the aqueduct, its flow, was dictated by a force both constant and subtle, gravity. To harness this force over dozens, sometimes hundreds of kilometers, to guide water across valleys and through mountains required a mastery of the gradient. This mastery was not achieved through intuition or guesswork. It was the product of careful calculation, meticulous observation, and, most importantly, of specialized instruments. In this chapter, we turn our attention to the essential tools of the Roman surveyor, the librator. We will examine the two primary instruments that made the aqueducts possible, the robust and reliable chorobates and the precise, versatile dioptra. Our most detailed understanding of these tools comes from the Roman architect and engineer Marcus Vitruvius Pollio in his foundational work, De Architectura. It is through his descriptions that we can reconstruct not only the form of these instruments, but also their function in the field. Let us first consider the chorobates. It was the workhorse of aqueduct surveying, a tool elegant in its simplicity and profound in its effectiveness. Imagine a long, straight beam of high-quality, well-seasoned wood, perhaps 20 feet in length, or approximately 6 meters. This length was not arbitrary. It provided a substantial baseline, allowing the instrument to span minor undulations in the terrain and derive a more accurate average level. At each end of this main beam, a leg was fixed, perfectly perpendicular to the top surface. These two legs were of equal length, supporting the main beam parallel to the ground. To ensure the rigidity of this 90-degree angle, diagonal braces ran from the ends of the main beam down to the legs, forming a sturdy trapezoidal structure at each end. The entire apparatus was built with care, its joints tight, its surfaces true. The chorobates functioned on two fundamental principles, providing the surveyor with a primary and a secondary method for establishing a true horizontal line. The primary method utilized plumb lines. From the top beam, directly above each of the two diagonal braces, a plumb line, or perpendiculum, was suspended. This was simply a weighted cord, typically with a lead or bronze bob at its end, shaped like an inverted cone. On the surface of the diagonal braces below, precise vertical lines were inscribed. When the chorobates was perfectly level, the two plumb lines would hang motionless under the pure influence of gravity, and their chords would align exactly with the inscribed marks on the braces below them. The surveyor would crouch, closing one eye to avoid parallax error, and observe this alignment. If the cord on the left hung slightly to the inside of its mark, and the cord on the right hung slightly to the outside, he knew the left end of the instrument was too high. The ground beneath it would be scraped away, or the entire instrument shifted, until both cords hung in perfect correspondence with their reference lines. Only then was a true level established. This system was remarkably accurate for its time. However, Vitruvius, a practical engineer, understood its primary weakness: wind. Even a gentle breeze, common in the open countryside where much of the surveying took place, could cause the plumb bobs to sway, rendering a precise reading impossible. The patient surveyor might wait for a moment of calm, but such moments could be fleeting. For this eventuality, the chorobates was equipped with a brilliant and utterly reliable backup system. Carved into the exact center of the top surface of the main beam was a long, shallow channel or groove. This channel might be 5 feet long and perhaps 1.5 inches deep. The essence of the Roman aqueduct, the very principle that allowed it to function across hundreds of kilometers, was not its monumental arches or its deep tunnels, but a concept of profound subtlety and relentless precision, the gradient. This was the gentle decline, an almost imperceptible slope engineered into every meter of the channel, from the distant spring to the final distribution tank, the Castellum Aquarii. It was the silent, invisible force that compelled the water on its long journey, a testament not to brute strength, but to a mastery of practical physics and meticulous surveying. The challenge was one of equilibrium. The gradient had to be steep enough to ensure a constant, cleansing flow, a velocity sufficient to prevent stagnation and discourage the proliferation of algae and other contaminants. A brisk flow also helped to carry some of the finer suspended sediments, keeping the channel, or specus, relatively clear. However, The gradient could not be too steep. An excessive velocity would be a destructive force, scouring the waterproof mortar lining, the opus signum, and eroding the very stone of the channel. High-speed water would exert undue pressure on turns and junctions, and upon its arrival at the city, it would be a turbulent, unmanageable torrent, difficult to slow and distribute. The Roman engineers, the liberatores aquae, or water levelers, therefore, had to find a precise and delicate balance, a perfect slope tailored to the specific volume of water, the length of the aqueduct, and the topography of the land it traversed. There was no single, universal gradient. Each aqueduct was a unique solution to a unique geographical problem. The celebrated Pont du Gard, a segment of the aqueduct of Nimes, exhibits an astonishingly shallow gradient, averaging just 1 centimeter of drop for every 36 meters of length, a ratio of approximately 1 in 3,600. This translates to a mere 25 centimeters of fall per kilometer. To maintain such a minute slope over a 50-kilometer course required an almost unimaginable level of precision. In contrast, other aqueducts, often those traversing steeper, more mountainous terrain, might employ a more aggressive gradient, perhaps a drop of 3 meters per kilometer, a ratio of 1 in 330. The average, however, tended to fall within a range of 0.15% to 0.30%, which is to say, a drop of between 1.5 to 3 meters for every kilometer of distance. This was the narrow window within which the Roman engineer had to work. The primary instrument for establishing this critical gradient was the chorobates. This was the undisputed master tool of the Roman surveyor. In its form, it was simple. A long wooden beam, perhaps 6 meters in length, supported by 2 legs at either end, with a top surface planed to be perfectly flat. On this top surface, a channel was carved. Before use, this channel would be filled with water. If the water level touched both ends of the channel simultaneously without spilling, the instrument was perfectly level. For added verification and for use in windy conditions that might disturb the water's surface, plumb lines were suspended from the top beam, hanging down past markings on the leg braces. When the plumb bobs aligned perfectly with their corresponding vertical marks, the chorobates was level. It was a simple, robust, and remarkably accurate device, a spirit level on a grand scale. The surveying process would have been a slow, painstaking progression across the landscape. The team of liberators would set up the chorobates and level it meticulously. They would then take a reading to a target staff, a vertical rod marked with gradations, held by an assistant some distance away. By raising or lowering one end of the chorobates using small wedges and observing the change in the water level or the plumb lines, they could establish a specific, desired slope. The conception of a Roman aqueduct did not begin with the quarrying of stone or the mixing of mortar. It began, as all great journeys do, with a single point of origin and a destination. The first and most fundamental challenge was not one of construction, but of calculation, a meticulous and demanding process of route planning and land surveying that would dictate the very feasibility of the entire endeavor. This initial phase, often overlooked in favor of the monumental arcades that remain, was a testament to the Roman mastery of practical geometry and their profound understanding of the unyielding laws of physics. It was a silent, slow, and deeply intellectual battle waged against the landscape itself. The process commenced at the source, the caput aquae. The selection of this source was a multifaceted decision, governed by 3 primary criteria: elevation, volume, and purity. Elevation was the non-negotiable prerequisite. As the entire system was to be driven by gravity alone, the source had to be situated at a significantly higher altitude than the terminus in the city, the Castellum Aquae, or distribution basin. The difference in height between these 2 points constituted the total potential fall of the aqueduct, a gravitational budget that the surveyors, or liberators, would have to carefully manage over many kilometers. Volume, or flow rate, was equally critical. Surveyors would observe a potential source over an extended period, ideally through all seasons of the year, to ensure a consistent and sufficient supply. A spring that gushed forth in the wet winter months but dwindled to a trickle in the dry summer was of little use for a city's unceasing thirst. They measured the flow using simple, practical methods, such as timing how long it took for the outflow to fill a container of a known volume. Purity was assessed through direct observation and empirical evidence. Vitruvius, the great Roman architect and engineer, provides guidance on this matter. Surveyors would examine the clarity of the water, the absence of silt or moss, and the taste. They would also observe the physical condition of the local inhabitants who drank from the source. Healthy complexions, strong limbs, and an absence of maladies were considered positive indicators of the water's quality. The presence of certain water-loving plants was also noted, as some were believed to thrive only in pure water. Once a suitable caput aquae was identified and approved, the immense task of charting a path to the distant city began. The ideal aqueduct would be a perfectly straight line, but the reality of terrain made this an impossibility. The primary goal of the surveyor was to plot a course that maintained a steady, gentle, and near-constant gradient. This gradient was the heart of the aqueduct's design. If the slope were too steep, the velocity of the water would scour the mortar lining of the channel, causing erosion and eventual structural failure. If the slope were too shallow, the water would become sluggish, allowing sediment to settle and block the channel, and potentially leading to stagnation and the growth of algae. The optimal gradient, though it varied between aqueducts, was often remarkably slight, sometimes as little as 1 meter of fall for every 3 to 5 kilometers of length, a testament to the precision of the instruments and the patience of the men who wielded them. The tools available to the Roman librator were simple in their components, yet highly effective when used with skill and care. The primary instrument for laying out straight lines and right angles was the groma. This device consisted of a vertical staff, upon which was mounted a horizontal cross. From the end of each of the 4 arms of the cross, a plumb line, a simple cord with a lead weight or plumb bob, was suspended. By sighting along 2 opposite plumb lines, the surveyor could establish a straight line of sight. The enduring legacy of the Roman aqueduct is not merely a testament to its hydraulic engineering, but also to the profound innovations in its material science and construction methodologies. The vast uninterrupted arcades and subterranean channels that traverse the landscape owe their very existence to a specific set of materials and techniques, honed over centuries of empirical refinement. At the heart of this structural revolution lies a single, remarkable invention, opus caementicium, or Roman concrete. This material, in conjunction with a sophisticated repertoire of masonry facings, form the fundamental building blocks of the aqueduct system. Opus caementicium was not simply a primitive forerunner to modern concrete. It was a composite material of extraordinary strength and versatility, possessing properties that, in some respects, have yet to be surpassed. Its composition was deceptively simple, consisting of 3 primary elements: a binder, an aggregate, and water. The true genius, however, lay in the specific selection and preparation of these components. The binder was a mortar made from lime, or calyx, and a special volcanic ash known as pozzolana. The production of lime was a meticulous process in itself. It began with the quarrying of limestone, a rock rich in calcium carbonate. This limestone was then subjected to intense heat, typically between 900 and 1000 degrees Celsius, in a kiln. This process, known as calcination, drove off carbon dioxide, converting the calcium carbonate into calcium oxide, a highly reactive substance colloquially known as quicklime. This quicklime was then carefully slaked by adding water, a process that produced a great deal of heat and transformed the calcium oxide into a fine, soft powder of calcium hydroxide, or slaked lime. This was the primary active ingredient in the mortar. The second, and arguably most critical component of the binder, was the pozzolana. Named for the deposits found near the town of Pozzuoli in the volcanic region of the Bay of Naples, this fine sandy ash was rich in reactive silica and alumina. When this volcanic ash was mixed with the slaked lime and water, a slow but powerful chemical reaction was initiated. The calcium hydroxide from the lime reacted with the amorphous silicates and illuminates in the pozzolana. This pozzolanic reaction formed a crystalline structure of calcium silicate hydrate and calcium aluminate hydrate compounds. Unlike a simple lime mortar, which hardens by reacting with carbon dioxide in the air, this new compound was a true hydraulic binder. It did not require air to cure and could, in fact, harden and gain strength while fully submerged in water. This property was revolutionary, allowing for the construction of durable piers in rivers, foundations in marshy ground, and, crucially for aqueducts, a core material that was fundamentally resistant to the degrading effects of moisture. The third component of opus caementicium was the aggregate, or caementa. This was not the carefully graded sand and gravel of modern concrete, but rather a heterogeneous mix of whatever hard, inert material was locally available. It could consist of broken stones, fragments of tuff, chunks of lava rock, recycled brick, or shattered pottery. The size of the aggregate varied depending on its position within the structure. Larger, fist-sized rubble was often used for the deep core of massive piers and foundations, while smaller, more uniform pieces were reserved for thinner walls or vaults. The application of Roman concrete was a laborious, layered process. Roman builders did not pour a liquid slurry, as is common today. Instead, they first constructed temporary wooden formwork to contain the shape of the desired structure. Within this shuttering, a thick layer of the pozzolanic mortar was spread evenly. Then, a layer of the aggregate, the caementa, was laid on top and pressed firmly down into the mortar bed, ensuring full encapsulation. The Roman aqueduct system, a monumental achievement of hydraulic engineering, was predicated on a single inviolable principle: the continuous, gentle, and gravity-powered flow of water. The maintenance of a precise and shallow gradient was paramount. This necessity, the very heart of the system's design, transformed from a simple surveying task on level ground to a profound engineering challenge when the carefully plotted course encountered a significant depression in the landscape. A valley, while inverted siphons, utilizing lead or ceramic pipes, were a viable, if maintenance-intensive, solution for some crossings. The preferred and certainly the most visually arresting solution was the construction of a bridge. Not merely a bridge for passage, but a bridge to carry water, a structure whose upper surface had to conform perfectly to the predetermined gradient, effectively erasing the valley from the water's path. The tool for this erasure, the fundamental unit of Roman monumental construction, was the arch. The true arch, as perfected by the Romans, is an elegant solution to the problem of spanning a void. Its genius lies in its method of handling weight. A simple horizontal beam, or lintel, placed over an opening bears the load above it through internal tension and compression, concentrating stress at its midpoint and its ends. It is inherently weak over long distances, prone to cracking and failure. The arch, by contrast, operates almost entirely in compression. The downward vertical force of gravity, acting upon the mass of the arch itself and any load it carries, is not resisted by tensile strength, but is instead resolved and redirected. This force is channeled outwards and downwards along the curve of the arch, through its constituent parts, into the supporting structures at its base. To understand the construction of an aqueduct bridge, one must first understand the anatomy of a single arch. The individual, wedge-shaped stones that form the curve of the arch are known as voussoirs. Each is cut with immense precision, their angled sides, or beds, designed to press tightly against their neighbors. The series of voussoirs begins at the springer, the lowest stone of the arch, which rests upon a horizontal surface known as the impost block. The impost, in turn, sits atop the pier or abutment, the vertical support structure rising from the ground or the riverbed. As the voussoirs are laid from both sides, rising towards the center, they form the arc. The final, central voussoir, placed at the apex of the arch, is the keystone. Its placement is the critical moment in the arch's construction. It locks all the other voussoirs into place, completing the compressive ring and making the structure self-supporting. The outward and downward force exerted by the arch is called thrust. This thrust must be contained. In a single isolated arch, such as a triumphal monument, this thrust is absorbed by the sheer mass of the abutments at its sides. In a multi-arched aqueduct, the thrust of one arch is counteracted by the equal and opposite thrust of its neighbor, a state of equilibrium that persists along the entire length of the viaduct until the final arch, whose outward thrust must be absorbed by a massive terminal abutment. The process of constructing such a bridge began not with stone, but with timber. After the foundations for the piers were laid, a process that could involve extensive excavation, the driving of wooden piles into soft ground, or even the construction of cofferdams to create a dry working area in the middle of a river, the piers themselves were raised. These were immense structures of cut stone, often ashlar masonry, or, more commonly, a core of Roman concrete, opus caementitium, faced with brick or shaped stone blocks. Once two adjacent piers reached the height of the impost blocks, the construction of the arch itself could commence. This was impossible without a temporary support structure known as centering. The gentle, almost imperceptible decline of the aqueduct channel, the very principle of its function, presupposes a landscape that is equally compliant. A steady, uninterrupted fall is the ideal, a theoretical line drawn across a perfect earth. But the earth is not perfect. It is creased and folded by valleys, and it is punctuated by the unyielding mass of hills and mountains. The Roman water engineer, the librator, could not simply will these obstacles away. The gradient, so meticulously surveyed with the chorobates and the groma, had to be preserved. When the path of least resistance was not a path at all, ingenuity was required. The aqueduct had to forsake the surface and travel either through the earth or, in a feat of hydraulic mastery, across the void. This is the story of those solutions, the patient darkness of the tunnel, and the immense, controlled pressure of the inverted siphon. When the surveyed line met a hill of moderate size, the engineer was faced with a choice: a long, contour-hugging detour around the landmass or a direct subterranean passage through it. The detour added significant length to the aqueduct, increasing construction costs, maintenance requirements, and the potential for structural failure over a greater distance. Tunneling, while immensely laborious and fraught with its own challenges, offered the sublime reward of directness. It kept the aqueduct shorter, safer, and its gradient more consistent. The decision to perforate the earth was therefore a pragmatic one, a calculation of labor against length, of immediate difficulty against long-term stability. The process began, as always, with surveying. The entry and exit points of the proposed tunnel were precisely marked. The alignment between these 2 points was then plotted over the hill's surface. This was a critical step, as any error on the surface would be magnified in the darkness below. Once the surface line was established, the true work could begin. The primary method was counter-excavation, digging from both ends of the tunnel simultaneously with the intention of meeting in the middle. This simple strategy halved the construction time. However, it doubled the potential for error. To maintain alignment and to facilitate the work, a series of vertical shafts, known as putae or cuniculi, were sunk from the surface down to the proposed level of the tunnel. These shafts, typically spaced between 30 and 60 meters apart, served multiple vital functions. Firstly, they provided ventilation, a constant supply of breathable air for the workers, or fossors, toiling in the confined space, and a means for the smoke and dust from their oil lamps and labor to escape. Secondly, they were portals for removal. The excavated rock and soil, the spoil, was loaded into buckets and hauled to the surface by winch and pulley, a slow but steady process of extraction. Thirdly, and perhaps most importantly, the shafts were instruments of alignment. By lowering a plumb bob, a perpendiculum, down 2 separate shafts along the surveyed line, the engineers below ground could establish a precise sightline. This allowed them to correct any minor deviations in their course, ensuring the two tunneling teams remained on a path to convergence. The shafts also provided additional work faces. Crews could be lowered into the shafts to begin digging outwards in both directions, meaning a single tunnel could be constructed from a dozen or more points simultaneously, dramatically accelerating the project. Inside the tunnel, the conditions were difficult. The space was narrow, often no more than 1 meter wide and 2 meters high, just enough for a single man to work the rock face. The only light came from the flickering, smoky flame of terracotta oil lamps, the soot from which can still be seen today, blackening the ceilings of surviving tunnels. The air was thick with rock dust and the exhalations of hard labor. We now turn our attention from the grand, visible arches and the subterranean tunnels to the very heart of the aqueduct system, the channel itself. This component, known to the Romans as the spicus, was the conduit through which the water completed its long journey. While less celebrated than the monumental bridges that carried it across valleys, the functional integrity of the entire aqueduct rested upon the meticulous construction and waterproofing of this simple yet critical element. The spicus was, in essence, the aqueduct. Everything else was merely structured to support it and maintain its precise, unyielding gradient. The construction of the spicus began after the survey line was established and the trench excavated, or the tunnel bored. Its dimensions were not standardized across the empire, but were dictated by the expected volume of water, the available materials, and a crucial ergonomic consideration. The channel had to be large enough for a maintenance worker to enter and perform repairs. A typical cross-section might measure approximately 1 meter in width and 1.5 to 2 meters in height, allowing a person to walk, albeit stooped, along its length. The outer structure of the spicus was most commonly fashioned from Roman concrete, opus caementitium. This remarkable material, a mixture of lime mortar, water, and an aggregate of stone rubble, was poured between wooden formwork. When a pozzolanic ash, or pulvis putiolanus, was incorporated into the mix, the concrete gained hydraulic properties, meaning it could set and harden even in the presence of water, making it ideal for this application. In other instances, particularly in earlier aqueducts or regions with abundant high-quality stone, the spicus walls or parietes were built from carefully cut ashlar masonry blocks laid in regular courses. More common, however, was a composite construction, a core of opus caementicium faced with brick, known as opus latericium, or with small, squared stones, known as opus reticulatum. This facing provided a more regular and durable surface for the subsequent, and most vital, stage of construction. Regardless of the structural material, the primary engineering challenge of the spicus was not strength, but impermeability. The constant flow of water under its own slight pressure would exploit any fissure or porous section, leading to significant water loss over the many kilometers of the channel's length. A leaking aqueduct was an inefficient aqueduct. To combat this, the Romans developed and perfected a specialized waterproof lining known as opus signinum. The creation and application of opus signinum was a multi-stage process requiring both specific materials and skilled craftsmanship. The primary components were straightforward: a high-quality lime mortar, sand, and the critical additive that gave the substance its name and its hydraulic properties, crushed terracotta. This aggregate consisted of pulverized pottery, roof tiles, or bricks. The fragments were sifted to a specific grain size, ensuring a consistent mixture. The genius of this composition lay in its chemistry. The silica and alumina present in the fired clay of the terracotta reacted with the free lime in the mortar in the presence of water. This is a pozzolanic reaction creating calcium silicate hydrate and calcium aluminate hydrate compounds. These compounds are insoluble and form a dense, crystalline structure within the mortar matrix, effectively closing the microscopic pores through which water might otherwise seep. The result was a hard, reddish-pink, waterproof cement. The application of the opus signinum was performed in layers. First, The interior surfaces of the specus, the floor or solum, and the walls, the parietes, were thoroughly cleaned and wetted. This was to ensure a strong bond between the structural wall and the first layer of plaster. The initial coat of opus signinum was often rougher, containing larger ceramic fragments. The successful conveyance of water into the city of Rome was an achievement of engineering. The administration of that water, however, was an achievement of bureaucracy. Once the aqueducts reached the city walls, their contents became a resource to be managed, a commodity to be distributed, and a system to be perpetually maintained. This immense task fell to a specialized institution known as the Cura Aquarum, the curatorship of the waters. In its structure, its legal authority, and its day-to-day operations, we observe the Roman genius for systematic control. During the Republic, the responsibility for water management was somewhat diffuse. It fell generally under the purview of the censors, who contracted for the construction and repair of aqueducts, and the aediles, who oversaw the distribution of water within the city itself. This system, while functional for a smaller city, proved inadequate as Rome's population and its corresponding demand for water swelled to unprecedented levels. The turning point came with Marcus Vipsanius Agrippa. As aedile in 33 BCE, and later as a private citizen acting with the authority of Augustus, Agrippa undertook a monumental reorganization of Rome's water supply. He repaired existing channels, built 2 new aqueducts, the Aqua Julia and the Aqua Virgo, and established a private workforce of 240 skilled slaves, the first dedicated familia aquaria, to perform the necessary maintenance. He understood that the aqueducts were not static monuments, but a dynamic utility requiring constant attention. Upon Agrippa's death in 12 BCE, this private workforce was bequeathed to Augustus, who in turn made them public property. This act formalized the transition to a state-run water authority. In 11 BCE, Augustus, with the Senate, established the permanent magisterial position of curator aquarum. This was not a minor administrative post. The first curators were senators of consular rank, men who had held the highest offices of the state. The post was granted for an indefinite period, often for life, and it carried with it significant legal and practical power, including the right to convene a tribunal and adjudicate disputes related to the water supply. The curator aquarum was, in effect, the water commissioner of the Roman world, a figure of immense importance to the daily life of the capital. The curator did not work alone. He was supported by a substantial and highly organized staff. This staff was initially composed of the public slaves inherited from Agrippa. However, the system was expanded significantly under the Emperor Claudius around 40 CE. Claudius established a second, parallel workforce, the Familia Aquaria Caesaris, an imperial corps of 460 specialists paid from the imperial treasury or fiscus. Together, these 2 bodies constituted the permanent, professional staff of the Cura Aquarum. Our most detailed understanding of this structure comes from Sextus Julius Frontinus, who served as curator aquarum at the end of the 1st century CE and wrote a comprehensive 2-volume treatise, De Aquis Urbis Romae, or On the Waters of the City of Rome. Frontinus provides a meticulous breakdown of the staff and their duties. At the top, directly beneath the curator, were 2 adjutors, typically senators of praetorian rank, who served as deputies. Below them was the professional hierarchy. The vilici were the overseers or foremen, responsible for the technical operations on the ground. They managed the work crews and inspected the aqueduct lines outside the city. Within the city, the castellarii were of primary importance. These were the keepers of the castella, the distribution tanks where the main aqueduct lines terminated, and from which water was channeled into the city's network of pipes. The castellarius was responsible for maintaining the tank, ensuring the correct gauges were in place, and keeping meticulous records of the water distributed. In the final years of the 1st century of the Common Era, under the brief and restorative reign of the Emperor Nerva, a man of distinguished consular rank was appointed to an office of immense, if often overlooked, importance. His name was Sextus Julius Frontinus. He was not an engineer by trade, nor an architect. He was a soldier, a governor, and a seasoned administrator, a product of the Roman senatorial class. In the year 97, he was made curator aquarum, the water commissioner for the city of Rome. The system he inherited was a marvel of the ancient world, a network of aqueducts that snaked for hundreds of kilometers across the countryside, a testament to generations of engineering prowess. But it was also a system shrouded in administrative opacity, rife with corruption, and suffering from decades of inconsistent oversight. Frontinus, a man of order and methodical precision, found this state of affairs intolerable. And so, he embarked upon a task that would secure his legacy far more enduringly than any military victory. He decided to understand the system, to measure it, to codify its laws, and to document its every function. The result of this undertaking was a unique and invaluable work, De Aquis Urbis Romae, on the waters of the city of Rome. It is not a work of soaring rhetoric or philosophical insight. It is, in essence, a guide, a manual, an administrative audit of one of antiquity's greatest infrastructural achievements. It is through this text, this meticulous and dispassionate report, that we can truly comprehend the protocols of the Roman water supply. Frontinus begins his work with a statement of purpose, one that perfectly encapsulates his pragmatic character. He writes that he considered it of first and greatest importance to familiarize himself with the business he had undertaken. There is no vanity here, only a sense of duty. He recognized that to effectively manage the aqueducts, he must first possess a complete and granular knowledge of them. This meant moving beyond the inherited and often inaccurate ledgers of his predecessors. He set out to conduct a comprehensive survey. He walked the lines of the aqueducts. He descended into their subterranean channels. He examined their sluice gates, their settling tanks, their distribution castella. He gathered all existing records, senatorial decrees, and imperial edicts pertaining to the water supply. His approach was empirical, data-driven, and relentlessly thorough. His treatise begins by systematically listing the 9 aqueducts that supplied Rome in his day. He details them in chronological order of their construction, providing for each a history and a physical description. The first, the Aqua Appia, built in 312 before the Common Era, was almost entirely subterranean, a practical measure to protect it from enemies during the Samnite Wars. Then came the Anio Vetus, drawing its water, as the name suggests, from the Anio River. Frontinus notes its low elevation and its often turbid water, rendering it less suitable for drinking. He then describes the magnificent Aqua Marcia, celebrated for the purity and coldness of its water, which flowed from springs far in the Sabine hills. He continues with the Tepula, named for its lukewarm water, and the Julia, an addition by Marcus Agrippa. He details the Aqua Virgo, another of Agrippa's projects, renowned for its soft water, and terminating at the baths on the Campus Martius. He mentions the Alciatina, an aqueduct of poor quality water, constructed primarily to supply the artificial lake for Emperor Augustus's mock sea battles, the Naumachia. Finally, he comes to the 2 monumental achievements of the Claudian era, the Aqua Claudia and the Anio Novus. These were the high-level aqueducts, their immense arcades striding across the Campagna, delivering vast quantities of water to the highest hills of Rome. The completion of an aqueduct, the final setting of its last stone and the first rush of water through its channel, was not an end but a beginning. It marked the commencement of a perpetual, low-grade conflict against the forces of entropy, geology, and human interference. The monumental structures, which appear to us as timeless and immutable, were in fact fragile, dynamic systems requiring constant, meticulous attention. The responsibility for this vigilance fell to a specialized corps of state employees known as the Aquarii. They were the sentinels of the water, the custodians of the flow, and their work, though largely uncelebrated, was as vital to Rome as that of the legionary on the frontier. The role of the Aquarii, their methods of inspection, and their patrol protocols form a critical yet often overlooked component of the Roman hydraulic system. The Aquarii were part of a larger administrative body, the Cura Aquarum, or the Office of Waters. Initially, during the Republic, maintenance was handled through ad hoc contracts let by the censors. However, with the expansion of the network under Augustus, the system was formalized. Augustus established the position of curator aquarum, a high-ranking senator responsible for the entire water supply. Under his authority was a permanent workforce, the Familia Aquarum. This workforce, as documented by the later curator Sextus Julius Frontinus, was comprised of hundreds of skilled and unskilled laborers. At its peak, under the Emperor Claudius, this public workforce numbered around 700 individuals. The Aquarii were the operational core of this familia, the men who physically walked the lines, inspected the channels, and provided the first line of defense against decay and disruption. They were organized into teams, assigned to specific aqueducts or sections of aqueducts, with their own stations, or stationes, and supervisors. This was not a military unit, but it possessed a similar structure of command and a deep sense of procedural duty. The fundamental task of the Aquarii was the patrol. Day after day, in all weather, teams would set out from their designated stations to walk the length of their assigned conduit. This was not a casual stroll. It was a systematic and highly detailed process of observation. The aqueduct was a linear system, and an inspector's gaze had to be trained to assess it both in its macrostructural form and in its minute details. For sections running above ground on arches, the patrol would begin at the foundations of the piers. The Aquarius would look for signs of subsidence, the slow, dangerous settling of the ground which could introduce stress fractures into the masonry above. They would examine the piers themselves for verticality using a plumb line or plumbum to detect any lean that might indicate foundational instability. The mortar joints between the massive stones were a key point of focus. Crumbling or missing mortar could allow water ingress, which, through freeze-thaw cycles and colder climes, could pry the very stones apart. They would look for fine cracks in the stonework, mapping their progress over time, noting whether they were static or growing. Moving their attention upward, they would inspect the arches and the superstructure that supported the water channel, or specus. The integrity of the vaulted arches was paramount. Any displacement of the voussoirs, the wedge-shaped stones of the arch, was a sign of critical structural stress. Atop the arches, the specus itself was the primary object of scrutiny. The inspectors would walk along the service path that often ran beside the covered channel, examining the exterior of the conduit. They looked for the telltale signs of leaks. The successful completion of an aqueduct was not an end, but a beginning. It marked the commencement of a perpetual, often silent, and largely uncelebrated struggle against the forces of nature and entropy. The engineered perfection of the gradient, the precise slope that coaxed water across vast distances, was a delicate state of being. It was a theoretical ideal that, from the first day of operation, was under constant assault from an insidious and relentless enemy, an enemy born from the very water the aqueduct was designed to carry. This was the challenge of maintenance, a continuous process of inspection and intervention, without which even the most magnificent aqueduct would slowly, inevitably, choke and fail. The primary internal antagonist was a phenomenon known as sintering. The water that filled the Roman aqueducts was rarely pure. Flowing from springs, it had percolated through limestone bedrock, becoming rich in dissolved minerals, particularly calcium bicarbonate. While invisible to the naked eye, this mineral load represented a latent threat. As the water traveled along the aqueduct channel, open in sections to the air and agitated by its own movement, a subtle chemical transformation occurred. The dissolved carbon dioxide, which held the calcium bicarbonate in solution, began to degage, to escape into the atmosphere. This shift in chemical equilibrium caused the less soluble calcium carbonate to precipitate out of the water. It did not do so as a fine powder that could be washed away. Instead, it adhered to the surfaces it touched, forming a hard, crystalline crust. This deposit, known to geologists as travertine and to the Romans simply as a persistent nuisance, is what we now refer to as sinter. The process was exceptionally gradual. a geological timescale operating within a human one. Layer by microscopic layer, the sinter grew. It coated the floor and the walls of the water channel, a slow petrification from within. The initial layers were often rough, providing an even better surface for subsequent crystals to form upon. Over years and then decades, these layers would accumulate, forming a thick, rock-hard lining inside the aqueduct's conduit. The consequences of this accretion were manifold and severe. The most immediate effect was a reduction in the channel's cross-sectional area. An aqueduct conduit designed to be, for example, 1 meter wide and 1.5 meters deep might, after 50 years of service, find its effective dimensions reduced by 20, 30, or even 50 centimeters of sinter on all sides. This constriction directly impacted the aqueduct's debit or flow rate. The volume of water that could pass through the narrowed channel was significantly diminished, leading to water shortages in the city it served. Furthermore, the surface of the sinter was not smooth like the original waterproof lining of Opus Signinum. It was rough and uneven, increasing the frictional drag on the water. This turbulence further impeded the flow, slowing the velocity of the water, even within the reduced channel size. The carefully calculated gradient, designed for a specific flow rate in a channel with a particular smoothness, was now interacting with a fundamentally different hydraulic environment. In extreme cases, the sinter could almost completely block a conduit, a form of arteriosclerosis on a civil engineering scale. Archaeological evidence from numerous aqueducts, such as the Pont du Gardon Nimes or the Great Aqueducts of Rome, reveals sinter deposits of astonishing thickness, concrete proof of this relentless process. In some abandoned sections, the channel is almost entirely filled, leaving only a small, fist-sized hole through which water once trickled. The sheer weight of these deposits could also pose a structural threat, adding many tons of unforeseen load to the arches and foundations of the aqueduct's superstructure. The successful operation of a Roman aqueduct was not a matter of its initial construction alone. It was, rather, a testament to a continuous, unceasing commitment to maintenance. An aqueduct, once completed, was not a static monument, but a dynamic, living system, subject to the perpetual forces of decay, geology, and the very water it was designed to carry. The chapter of its life dedicated to routine repairs, to the mending of leaks, and the reinforcement of its structure was perhaps the longest and most critical. This was the domain of the Cura Aquarum, the public office responsible for the water supply, and its dedicated workforce of engineers and skilled laborers, the Aquarii. Their work was not one of dramatic invention, but of meticulous, repetitive, and essential preservation. The primary and most relentless antagonist in the interior of the aqueduct channel, or specus, was the water itself, specifically the minerals dissolved within it. Roman water sources were often hard, rich in calcium bicarbonate. As this water flowed along the channel, changes in pressure and temperature caused the dissolved minerals to precipitate out of the solution, forming a hard, crystalline deposit of calcium carbonate. This substance, known to geologists as travertine or calcareous tufa, and to the Romans simply as sinter, was the aqueduct's constant internal threat. The accumulation of sinter was a slow, inexorable process. It would begin as a fine, rough film on the waterproof lining of the channel, the Opus Signinum. Over years and decades, this film would grow into a thick, rock-hard crust. The process was not uniform. It was often thicker on the floor and lower walls of the channel, and its rate of deposition varied depending on the mineral content of the specific water source and the velocity of the flow. A slower current allowed more time for the particles to settle and adhere. The consequences of this buildup were twofold. First, and most obviously, it reduced the hydraulic capacity of the channel. A channel designed to carry a certain volume of water would see its cross-sectional area steadily decrease, constricting the flow and diminishing the supply to the city. Frentinos, the curator aquarium in the late 1st century, meticulously documented the design capacities versus the actual delivery, and a significant part of this discrepancy was attributable to such incrustations. The second consequence was structural. Center is dense and heavy. As layers upon layers accumulated over miles of elevated arcade, the sheer weight added to the structure was immense, placing additional, unplanned stress upon the arches and their supporting piers. The removal of center was therefore a fundamental and recurring maintenance task. To perform this work, a section of the aqueduct had to be taken out of service. In systems with multiple aqueducts supplying the city, this could be managed by diverting water and relying on the other channels. For a solitary aqueduct, it meant a temporary but complete shutdown of the supply. The Aquarii would enter the channel, often through inspection shafts, or puttae, spaced along the route. Their tools were simple and robust. Heavy mallets, iron chisels, picks, and the ubiquitous Roman military pickaxe, the dalabra. The work was arduous. The center had to be manually chipped away from the channel walls and floor. It was a task requiring both strength and care. A careless blow could fracture the underlying opus signatum lining, creating a new leak that would require a subsequent, more complex repair. The workers would break the center into manageable chunks, which were then hoisted out of the inspection shafts or carried out of ground-level sections. These removed blocks of center were not always treated as waste. The material, once extracted, was a form of solid travertine and was often repurposed as a building material, particularly for smaller constructions near the aqueduct line. The journey of the water, having been meticulously guided across vast expanses of countryside, through tunnels carved in rock and over valleys on monumental arcades, does not conclude upon its arrival at the city walls. Rather, it enters its final and perhaps most intricate phase, the distribution throughout the dense urban fabric. This terminal stage of the aqueduct system begins at a specialized structure known as the castellum aquae, the water castle, which serves as the nexus between the long-distance conduit and the localized network of urban pipes. It is here that the singular, massive flow of water is divided, measured, and directed to its various endpoints, transforming a feat of macro-engineering into a vital element of civic life. The castellum aquae, or main distribution tank, was typically a substantial and often architecturally significant building located at a high point within the city or just outside its gates to leverage the remaining gravitational potential energy of the water. Constructed of durable masonry and lined with waterproof opus signatum, a concrete incorporating crushed terracotta tiles, these structures were engineered to withstand the constant pressure and flow of a major aqueduct. Upon entry into the castellum, the water's velocity, which had been carefully maintained throughout its journey, was deliberately slowed. The initial chamber often functioned as a settling basin, or a series of such basins. Here, any remaining sediment, grit, or suspended particulate matter that had not been deposited in settling tanks along the aqueduct's route would precipitate out of the now slow-moving water. This primary clarification was crucial for preventing the blockage of the much smaller downstream pipes and ensuring the potability of the supply. The process was one of simple decantation, allowing gravity and time to purify the water one last time before its final dispersal. From the settling basins, the clarified water would flow over a weir into the main distribution chamber. This central element of the castellum was the heart of the urban water system. It was here that the fundamental decisions regarding allocation were made manifest through precise hydraulic engineering. The Roman engineer and architect Vitruvius, in his work De Architectura, outlines a canonical design for this chamber. He prescribed a system of 3 primary outlets, or calyces, leading from the main tank. These bronze nozzles were set at 3 distinct elevations. This hierarchical arrangement was not accidental. It was a deliberate reflection of Roman civic priorities and social structure. The lowest of the 3 outlets was dedicated to supplying the public fountains, the lacus. By placing this outlet at the bottom, the engineers ensured that the fountains would receive water continuously, even in times of drought or reduced aqueduct flow. The supply to the general populace was considered the most critical function of the system, a non-negotiable public good. The middle outlet was positioned to feed the great public baths, or thermae. These vast complexes were prodigious consumers of water, essential to Roman hygiene and social life, but they were deemed secondary to the basic needs of the population. The revenue generated from bath entrance fees also provided a source of income that could be directed towards the maintenance of the aqueduct system itself. The highest outlet was reserved for private users, the wealthy citizens who could afford a direct connection to their domus. This supply was a luxury, a privilege granted by the emperor or sold at a considerable price. By being at the highest level, this was the first supply to be cut off if the water level in the castellum dropped. This tripartite system thus created a robust, default hierarchy of distribution, ensuring that in times of scarcity, the needs of the public would be met before the luxuries of the few. The story of the Roman aqueducts does not conclude with the completion of the last great channel, nor with the final calibration of aquaribates on a dusty plain. Its final chapter is a slow, protracted narrative of physical decay and intellectual transmission, a story written over centuries in crumbling mortar, repurposed stone, and the faint, persistent memory of engineering principles. The decline of this vast hydraulic network was not a singular event, but a gradual unwinding, a process deeply intertwined with the broader structural transformations of the late Roman world. In the Western Empire, the 3rd and 4th centuries witnessed increasing political instability and economic strain. The constant pressure on the frontiers demanded immense military expenditure, which in turn strained the imperial tax base. The sophisticated bureaucracy required to manage large-scale public works, including the Cura Aquarum, the special commission overseeing Rome's water supply, began to show signs of stress. Funding for routine maintenance, once a state priority, became intermittent. The core of specialized state-owned slaves and freedmen, the familia aquarum or Aquarii, who possessed the generational knowledge of cleaning, patching, and surveying the lines, slowly diminished in size and expertise. Small breaches, which in the 2nd century would have been repaired within days, might now be left for weeks or months. The insidious accumulation of calcium carbonate, the hard center deposits that gradually constricted the flow within the spicus, was addressed with less frequency. This meant a slow but measurable reduction in the volume of water reaching the cities, a subtle decline that preceded the more dramatic disruptions to come. The critical turning point for the aqueducts of Rome itself arrived in the 6th century, during the Gothic Wars. The protracted conflict between the Ostrogothic kingdom and the Byzantine forces under the general Belisarius turned the Italian peninsula into a battleground. In the year 537, during the siege of Rome, the Ostrogothic king Witiges made a strategic decision to sever the city's water supply. His forces systematically identified and broke the aqueduct channels outside the city walls. The Aqua Traiana, the Aqua Appia, the Aqua Marcia, the Annio Novus, all were rendered inoperative. This was not a subtle act of neglect, but a deliberate act of engineering warfare. For the first time in centuries, the great baths fell silent, the monumental fountains ran dry, and the populace was forced to rely on the Tiber River and the city's ancient wells. While Belisarius's forces eventually prevailed and some attempts were made to repair the lines, the damage was both physical and psychological. The city of Rome had suffered a catastrophic demographic collapse, its population plummeting from a peak of over 1 million to perhaps less than 50,000. The vast quantities of water supplied by 14 aqueducts were no longer necessary for such a diminished population. More importantly, the centralized state apparatus with the economic resources and technical skill to restore and maintain such monumental infrastructure had effectively ceased to exist in the West. The aqueducts were not so much destroyed as they were abandoned. The cost of repairing dozens of kilometers of breached arches and tunnels for a city that no longer required the water was simply beyond the capacity of the post-Roman authorities. What followed was a slow process of natural reclamation and human salvage. Over the ensuing centuries, the abandoned structures became a part of the landscape. Frost and rain weathered the mortar of the opus caementicium. Plant roots, particularly those of figs and ivy, worked their way into microscopic fissures, slowly and relentlessly prying the structure apart. And so, as the aqueducts fell silent under the Roman moon, let your own thoughts now begin to quiet. The meticulous work is done. The steady, gentle gradient has brought us to our destination, a place of rest. Thank you for joining us on the Whispered Lore. It is time to drift into your own peaceful slumber. Rest well. Sleep deeply. Good night.